So this video is going to cover the conceptual approach to finding distances between things in 3D. At this point, you need to kind of have a good understanding of how to come up with the vector equation for a line, and what the general equation for a plane looks like, because we're going to be using those things to kind of calculate the following. And we're going to do some different combinations of things. We're going to figure out the distance between, we'll start with like a point and a plane. So a point to a plane, maybe then we'll do like a plane to a plane. So plane to plane. Then we'll do a line to a plane. Line to plane, we'll do maybe two lines in 3D space, line to line. And then we will cover a point to a line. And that's pretty much all the different combinations of things that we could get. So these are all going to be conceptual approaches. There's not going to be any concrete solved versions. There are a lot of solved versions in the textbook if you just crack open the section where it talks about coming up with the equations of lines and planes in 3D space. There's a bunch of workout examples. So these are just going to be the theory, because once you understand the theory, right, it makes sense. And my suggestion for every single problem, no matter what it says, is to draw a picture of what's going on. So, for instance, in this very first example, when we're doing the distance between a point and a plane, all I'm going to do is I'm going to sketch a picture of a plane. And I'm going to give myself a point kind of floating around in 3D space. I don't know, I'll just call this point X, Y, Z. And if we have the equation of this plane, it's going to be Z is equal to, something with an X plus something with a Y plus some number. Okay, so we'll have the equation of the plane as well. And the question is, how do we find this distance? And so the theory is that first and foremost, what would represent the distance between a point and a plane? Well, that's going to be visually represented, not just by any random line, but it's going to be a line that exists perfectly orthogonal or at a 90-degree angle to the plane, right? So this orange line is going to represent basically the shortest distance that we're looking for. Now, this would be really easy if I happen to know, right? Like if I could come up with this line, if I could prove that it was at a 90-degree angle, and ultimately if I could figure out what point this was that this magical line that I just created intersects this plane, because then I could just use the distance formula to calculate the distance between those 2 points. But that's not really possible because this line is in theory, the shortest distance, but coming up with it is kind of non-trivial. But we can kind of get around this in a cool way, because every single plane, no matter what plane it is, has a normal vector. So let's say that this little pink thing right here is my normal vector. And I can pick up this normal vector. Remember, I can snag it and I can move it around wherever I want. It's still the normal vector for the plane. And so I could go and I could put it right on top of this orange line, pretend those are, kind of in the same way. And the strategy for doing this particular problem is we're going to pick a random point that exists on this plane. We're going to pick some point, X naught, Y naught, Z naught, and we're going to draw a vector between that point and the point that we were given. Okay, we're going to draw this vector. I'm going to call it the vector A, if you will. And the key thing here is we need to remember, all the work that we've done so far with dot products and projections, because if you're very clever about this, what this is, right, this orange line that I had just drawn earlier is the result of if we take the vector A and we project it in the direction of the normal vector n, right? So what we have here in orange, that right there, is equal to, technically it's the component of A projected in the normal direction, right? You take the projection, you project A onto n, and we just want the length. And we're going to get it, right? Because you can kind of see that no matter what yellow point I picked, we're always going to be able to form this nice right triangle. And if we remember how projections work, right, this is how we, do these projections. And so this formula, you just need to kind of remember what this formula is to then be able to solve this. This formula is just going to be a dot our normal vector, which we will be able to get from the equation of our plane, divided by the magnitude of the normal vector, right? And yeah, that's pretty much it. This is it. This is the little formula for doing this. Now, I don't recommend that you just memorize this formula, because as you can tell, there's a bunch of different cases, and what you're going to be using to solve these problems will vary between the different cases. So this is the first case. This works in all of them. So you'll be given a point, you'll be given the equation of a plane, and you just find the distance between the point to the plane in the following fashion. Draw a picture and make sure your picture is nice and neat. Use different colored pens, whatever it is that you need to make it happen. So we're going to take this, we're going to get rid of it, and we're going to go on to the second example. So maybe I'll just erase this. We covered that one. So we're going to do the distance between a plane and a plane. So there's two situations, right? If we have two planes, the only way that there's going to be distance between them is if the planes are what? Right? Is there going to be distance between them if the planes look like this? Absolutely not, right? The planes are going to intersect at some point, and the distance between them would just be 0. So the only way for the two planes to have distance would be if they exist kind of parallel to each other. Not kind of, they have to be parallel to each other. And just as a reminder, right, when are two planes going to be parallel to each other, right? Remember, the general equation of a plane is like a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and all of this is equal to 0, right? The equations of the planes, are going to vary, but their normal vector will either be the same or they will be some multiple of each other. So when you look at these, you should see that, here's a normal vector kind of pointed up like so. There's some n, and maybe this one has a normal vector and it's way longer, but it's pointed in the same direction, right? Basically, these normal vectors are parallel to each other, and that will give us that these planes have to be parallel. And so then from there, it's basically like the example we just did. You just, you're going to have the equation of two planes. You pick any point on this plane, pick your favorite one, x, y, z. How do I pick a point, right? If I have a plane like, 2x plus 3y is equal to z, how do I pick a point? You pick a value for x, you pick your favorite value for y, and then you see what z has to be to make sure that this point actually lies on this plane. You'll pick a point there, and we do the same approach, right? This bottom blue plane has a normal vector of some sort, right? It has some normal vector n. I can pick a point that exists on this blue plane, right? X naught, y naught, z naught. I can draw a vector between these 2 points, and maybe I'll try and make my drawing a little bit more accurate here. Right, I'm going to draw this vector between those 2 points. It's going to look something like this. And if I project this new vector that I've made, call it A, in the direction of n, it's going to give me, right, some new vector like that. And if we just take the component, again, we'll just do the component of A in the direction of n, and that's going to give me the length that we are looking for right there. And this will work because all of these points, no matter which one I pick on this plane, they're all going to be the same distance from the other plane, from the bottom plane. And so this will work. So that's essentially how you do the distance between two planes. Relatively straightforward, very similar to the other example that we just did. All right, so let's cut this. All right, let's erase this. Oops. Okay, so how do we do from a line to a plane? Okay, so let's figure this one out. So we're going to, again, create the equation of a plane. All right, so there's our plane. Now another reminder, right? This line has to be kind of parallel to this plane, right? Otherwise, the line's going to be doing this at some point, and the distance between the line and the plane is going to be 0. So our line, whatever it is, has to kind of exist up above this plane, kind of floating around in space like this. Now, this problem's a little bit trickier in the sense that I can pick a bunch of points on this line, and they're all going to have, various right angle distances to this plane, kind of depending on where that point is that we pick. And so the question is, how do we make sure that we pick the correct one? Like that, how do we do this measurement? Well, the nice thing is that technically speaking, if I pick a point, it looks like they all have different right angle distances, right? It looks like what I just said is true, but technically, remember, this line has to be floating more or less kind of parallel to this plane. That, in other words, the direction vector for this line, right? If I say this is my direction vector v, I should be able to pick it up. I should be able to pick it up and place it down here on this plane, right? I should be able to pick up and drag it. It has to be parallel, because if it's not, then the line and the plane are going to intersect, which means that technically speaking, if I draw this right angle distance down from any point that I choose, right, no matter which point that I pick, it's going to be the same distance between the line and the plane no matter what. And then, well, we're going to take a very similar approach, which is, okay, well, I have the equation of the line. I can pick any point on it I want, call it x, y, z. I'm going to pick a point that exists on this plane, x naught, y naught, z naught. I'm going to create a vector going between the two, like so. And once again, I'm going to project that vector in the direction of the normal vector for this plane, like that. And, these create right angles no matter what we pick. And so it's super slick. We get to use the same process for basically these first 3 examples, and it's not too bad. Okay, so that's the first 3. So let's select all this. Let's get rid of it. Cut. We'll get this. All right, line to a line. Now, this one's a little bit trickier. Why is this one trickier? Well, because, the odds of a line intersecting another line is not very, it's not very big, right? There's a line, right? There's a line, and we're going to have to use our imagination that the distance between these two, right, that there's a gap, right? That if I pick this point, that we'd go down here, and that they're not all equidistant to this blue line, right? That's hovering above the blue line, if you will. Okay, and so the question is, how do we do this? Now, this one's a little bit trickier because it's not as easy as, I just pick a random point and then get a normal vector, because there isn't like a normal vector to these lines, right? There are a bazillion vectors that all kind of go around, that it all exist at 90 degrees to this line, right? It's basically anything that's orthogonal, and I can spin it around these lines. And so we have a little bit of an uphill battle in trying to brainstorm what it is that we can do. And maybe just to help, the visual, I know that they're supposed to be spaced apart, but I'll draw this one just a little bit under, so it looks like maybe there's more of a gap. Okay, so there's the 2 lines, right? They're floating around in space. There's space under it. And if I were to just pick 2 random points between them, right, and draw a vector here, it doesn't really work. But the strategy is, well, we know still, right, what has to be true if we're talking about the distance between these lines, or rather the shortest distance between these lines. If we're talking about the shortest distance between these lines, that means that there is some point on the first line and some point on the second line where I could draw this dashed line between them. And what is going to be true about this dashed line? If this is the shortest distance between these 2 lines, this dashed line is going to exist at a right angle to both of these lines simultaneously. Okay, now that's not the case for every single one, right? If I were to pick a random point here and, do this and to say, that's the shortest distance, you can kind of tell that this is not a right angle. maybe it's a right angle over here, but it's not a right angle on this one, so it's not going to be the shortest distance. And so it's really important that we keep in mind that the shortest distance happens at right angles. And so basically, this wouldn't be too bad, right? Like if we tried to follow a similar approach where I say, okay, pick a point on the top line, I call it X, Y, Z, right? Pick any random point on the second line, call it X naught, Y naught, Z naught, right? Create a vector between them, right? And you're like, well, the strategy in the last one was to do what with this vector A? Well, the strategy was to project it onto some normal vector. But the problem is we don't have a plane where there's just one normal vector. There's infinitely many normal vectors. However, there is only one normal vector that is orthogonal to both of these lines. And that is the normal vector that we want to pick. We want to pick this special normal vector n and project A in the direction of this vector n, because whatever this length is that we get is going to be the shortest distance between those two lines. And so the question really boils down to, well, how do I get this n, right? How do I create this vector that is orthogonal to both of these lines? Well, how do I create an orthogonal vector? And the thought that should come to mind is, well, it's probably going to have to do something with the cross product, right? It's going to have something to do with the cross product. And sure enough, right, the cross product says if I have two vectors, u and u cross v, it's going to poop out some new vector, some normal vector that is orthogonal to both of those. So then it's like, okay, I want to create a normal vector. What u and v do I use? Well, I'll tell you what, this bottom line here has a direction vector, right? It has a direction vector built into this line. Call it u, if you will. And the top one has a direction vector. Call it v, right? And maybe I don't even need to draw them there. I can pick them up and draw them anywhere. But this one has a direction vector v. And if I take the cross product of those direction vectors, what will I get? I am going to get a vector that is orthogonal to both of those lines. It's going to create this vector n. And so the idea here is step one, right? Step one is to, use the direction vector u and v to create the normal vector n, and then step two is to do our projection business, right? Then it's project A onto n, or rather, I guess this should be the complement, or excuse me, the component of A in the direction of n, right? We just want that length, okay? And just keep in mind, sometimes you'll do this operation where you're solving for the component and you'll get a negative answer. Just make sure that all your answers are positive. Take absolute values because we're talking about distance when we're doing this. We want to make sure all our distances are positive. But yeah, that's it. So there's just one extra step, but this one took a little bit of extra heavy lifting, right, to logic our way through it in terms of how do we come up with that shortest distance. So again, we drew the equation of two lines. We said, okay, the shortest distance is if I were to create an orthogonal line to both of these existing lines. Okay, so it's got to be, normal. It's got to be orthogonal to both lines. How can I do that? Oh, we took the cross product of the direction vectors for both lines, created n, and then projected a random vector A onto that normal vector. I guess it's not really a random vector A. It's created from any point on either of the lines, and we just create A like so. So that's that one. So we're almost done. Okay, and I guess the last example, what do we have? Point to a line. Okay, so how do we do it for the distance between a point to a line? So let's see. Let's try and logic our way through this. So here's a line. Okay, there's some line. And we have some point floating around in space. Call it X, Y, Z. And again, what's a good idea? Well, we know that we would like, we really want this particular distance here, the one that exists orthogonal to the line. Okay. And so now the question is, all right, well, I need something that's normal to the line, but again, the problem is, right, there's a bazillion normal vectors, right? This is a normal vector, even this is a normal vector if I sketch it, right? And this is a normal vector because, it's going to exist at this right angle. Well, if I could draw it better, it's going to exist at a right angle kind of going this way, right? There's a bunch of normal vectors that as I kind of rotate them around that I could get, and not all of them are going to result in the shortest distance, right? If I project something in this direction, we're not going to kind of get what we're looking for. So the question is, how do we do it? So let's kind of take a similar approach. Let's see. So what happens, right? We're just brainstorming how to do this. What happens if I take a point here, x naught, y naught, z naught, and we say that we still want to do the same thing we did before. So we draw a vector between these points. We call it A, and say, gosh, if only I could come up with the normal vector that happens to go between our pink point and this orange line. Well, this one's a little bit more challenging. But, we can, maybe notice something else, which is, again, this line has a direction vector, right? This line has some direction vector. I'm going to call it, I'll call it the vector v. And what do I know about this vector A and this vector v that I've just created? Well, that they're going to create some angle theta, right? They create some angle theta. And in this particular case, we may not be able to create a normal vector like we were in any of the other examples, but we, using our trigonometry knowledge, we know that we're just trying to solve for this side of some right triangle, which means that, if I call this side, I don't know, let's call it D for distance, if I'm trying to solve for that, and the red side, right, is going to be the length anyways, is going to be the magnitude of A, we could set up a trig equation, right? What trig equation involves the opposite side and the hypotenuse? Well, that's going to be sine of theta. So we know for a fact that sine of this angle between those two vectors is equal to D over the magnitude of A. Or in other words, that if we're solving for D, this is going to equal the magnitude of A multiplied by sine theta. And so behold, right, we have a little formula that we've just come up with where we can solve for the answer as long as I know the angle between these two vectors. As long as I know the angle between the vector A and our direction vector V, we should be good to go. And I should specify this is the acute angle. Don't forget that sometimes when you do this work, you'll solve for theta here. That is the obtuse angle. We want to use the acute angle between those two vectors. And so, well, how do we solve for theta? We have a couple tools to do that, right? One would be to use the dot product, right? We know that if I do A dot n, this is equal to the magnitude of A times the magnitude of n. Oh, not n. What are we using? We're using v for a direction vector. A dot v would equal the magnitude of A times the magnitude of v times cosine of the angle between them. So I could solve for theta because in theory, I know what A is, right? I created A. V is part of the line. I can solve for this magnitude, solve for that magnitude. And then how do I get cosine? I move this stuff over to the left side, and then I use the inverse cosine on both sides to solve for theta. And then once I have what my angle is, I can plug my angle here, calculate sine of it. I can solve for D, right? I could do this, be a little messy, but we could do it. Okay. Now, thankfully, there is one more formula that we have at our disposal that uses sine theta, and it even has a magnitude of a vector in it. And that formula, so our second option for doing this, which in my opinion is the better option, is to remember that if we consider the magnitude of the cross product of A and V, that there's a formula that says this is equal to the magnitude of A the magnitude of A multiplied by the magnitude of V times sine theta. And if we're, just being patient for a second, why am I showing you this? Because A sine theta, the magnitude of A sine theta is what D equals. That's what we're solving for. So it turns out that solving this problem is just, we take this and rearrange it, And if we find the magnitude of the cross product of A and V and divide it by the magnitude of V, we're going to get the magnitude of A times sine theta, which is the distance d that we are looking for. So I could go through this process and I could do the dot product. I could find these magnitudes. I could use the inverse cosine, solve for theta. I'm going to probably get some nasty decimal. I could plug in that decimal into sine theta, probably get another nasty decimal, right? Our answer is going to kind of become diluted as we go. Or we just solve for this cross product, which, shouldn't take too long, right? This is going to, create a vector. Then we take the magnitude of that resulting vector, divide it by the magnitude of V, and we are done. That's it. Easy peasy. Okay, so that's it. Those are like some 5 different examples of finding distances between things. Not too bad. Yeah, just big takeaways. If things are parallel, they're going to have distance. If they're not parallel, if you have like a line and a plane, for instance, then they're not parallel. They're going to intersect at some point. The distance is 0. To be successful in doing these just requires to come up with sketches. So I would suggest, if you're going to do problems, that kind of solve for any of this stuff, I would keep this video by your side. But because you may have a quiz on something like this, or you may just inherently want to get better at thinking in 3 dimensions, I would practice, sketching out the shapes that you've been given and see if you can come up with the processes on your own. Right? Draw yourself some vectors, make some mistakes, screw up, forget what you're supposed to be doing, and then come back to the video. And again, if you're the type of person who's just going to try and memorize these formulas for every individual approach, I don't recommend that, just because there's so many different types of questions you could be asked. I would go to it, and as soon as you get what you need, like the little nudge of like, oh, create a normal vector, or oh, create, the vector A going between 2 points or something, and like that's the nudge you need, put the video off to the side and try to finish the problem on your own, using what you remember about your dot products and your cross products and your projections and all of that good stuff as well. So yeah, this is an application of, the stuff we've been learning about lines and planes in 3-dimensional space. Hopefully it was interesting, and I'll catch y'all in another one soon.